Okay, the focus of this lesson is going to be electric force. You just want to go through concepts around it, and then we're going to be calculating things relating to it. Okay, so we are bracing ourselves for this new thing. Let's go ahead. Now, first thing I would want to just remind you is that this force, this electric force, is just a force like any other force that you studied before. Okay, remember that in your last semester, you studied the force on a spring, right? Or the force by a spring. Okay, and you also studied about the gravitational force, right? Where we used to call it weight in high school. And then when we came here, yes, it's still weight. I mean, the gravitational force is still weight, but we were referring it to more as just the gravitational force, the force due to gravity. Okay, and that's the force that keeps us all on the earth. Now we are talking about another force, just like those two. We also talked about frictional force. Yeah, we also talked about frictional force. And if you see, all the forces we were studying, we were working with, we would then calculate their values, we would quantify them, we would find a formula for them. So that means at the end of this, we must have a formula for this electric force. Okay, we must know that it exists, so that when we work with situations where it's there, we can know it's there. But not only know it's there, also find its value. Okay, so we're going to know about this. We have to know the situations where it acts, and then we are going to be able to then quantify it, give it a formula. All right, so here's a quick a quick prelude, okay, to this idea of electric force. Preliminary prelude. First we'll talk about the force, just a quick rundown through what a force is, the types of forces, and then we'll see where this guy fits in. So a force, if you see the definition I put, is a push or a pull that is acting on an object. So it's a push or a pull. It can be pushing it forward or pulling it backwards, right? As a result of its interaction with another object. So forces are caused by two objects interacting. Forces will be acting between two objects. Okay? When a motion or shape, it can change the size, it can change the shape, and it can change the motion of a body. Now, I said forces are caused by two things, two objects. We use the word object, okay, in physics. Two objects. In chem, we use the word particle. In bio, we use the word organism. Here we talk about two objects interacting. Now, the two objects may be in contact, or they may not be in contact, as you're about to see here. Then that is what we use to group our forces into these two categories: one, contact, and two, non-contact. Okay, the force is acting between two objects, definitely. But contact forces now, they arise from physical contact between the objects. So the force between these objects will only be there when these two objects are physically in contact. And the force will be acting between the surfaces of these two objects. Like friction. A box that you're dragging on the ground should be in touch with the ground. Okay, and then the surface of the ground and the surface of the box will be exerting force on one another. Now here, field forces. What are field forces? Field forces, these ones are those that act over some distance. The two particles don't have to be in contact. Okay, there is no need for physical contact. They act over some distance. Now if you look at examples, what are examples of contact forces? Friction, buoyancy, which acts in fluids, or especially in liquids. When you put something in water, you push it down and then it is pushed back up. It's like upthrust, right? And then what else do you have? You have the force that is caused when you're pulling, like tension. It's caused by ropes and cables. When you pull, it's a pulling force. Now for field forces, we deal with three of them, which we're going to study extensively. Three field forces, major, because we have three major fields. That is the gravitational field, electric field, and magnetic field. So we're going to talk about those guys. I don't want to talk too much about them because our focus here is on electric force. But field forces come from the three fields. Okay? These field forces, these three that I've talked about, the gravitational force, weight. If you see a plane when it crashes, what makes the plane fall onto the earth or come back down is the force due to gravity. Okay, the weight. We normally say the weight of the airplane, but weight corresponds to it's just the force. Weight is just the force due to gravity, and it's caused by the mass of the people in that plane or whatever. What makes it fall down? Is the earth in contact with the airplane? No. Okay, the ground of the earth is far away from the plane, but it still falls back down to the earth because gravitational force is a field force. They don't have to be in contact. Okay, what else? The magnetic force. Magnetic force, you see that it is when you have a charged particle that is moving, and then here we are dealing with an electric force, which is what we're going to be dealing with. Now let's focus more on our electric force, and let's just do it, see how to calculate it, and we'll be done. Electric force, what is it and where does it act? It is the force of attraction or repulsion. So point number one, electric force can push or it can pull. It's different from gravitational force. Gravitational force only pulls. Tension only pulls because you can't push with a rope. Tension is in ropes and cables. It can only pull. But electric force can pull or push. Okay? It is the force of attraction or repulsion that acts between electric charges. So, electric force acts between charges. When we say charges, we mean charged particles. The electric force is the force that is between two charged particles. Okay? And that force is called the electric force. It can be attractive or it can be repulsive. It can pull or it can push. Charges interact with each other through electric force. That's what we've just been saying. Now, let's see in point number two. It acts over a distance. It's a field force. The two charges don't have to be physically in contact. They can be far away from each other, meters away from each other, and this force will still be acting. It acts over a distance and is responsible for interactions between charged particles. It is the reason why this electric force is the reason why we see the things we see. Let me tell you what we mean by interactions. Here are the interactions. One was like charges repelling and opposite charges attracting. We have observed that when you bring two things that have the same charge, they repel one another. They go opposite directions. But if you bring two things that have different charges, they will attract. Okay, they will go towards one another. And the reason why that is happening is because there is a force. There is a force acting there that is attractive or repulsive. Okay? When is it repulsive? It is repulsive when the two charged particles have the same charge. Whether both of them are negative or both of them are positive. If they have the same charge, they will repel one another. Negative and negative will repel. Okay, it's like that. They will repel. So what is causing that is the electric force. So we are now already saying electric force is the force that acts between charges. So if you get a situation and you see charged particles, the force there, the force you are calculating is the electric force. Okay? Is the electric force. We'll talk about magnetic force when these charged particles start moving. But here we are just talking about charged particles being there. Just their presence. They don't have to move. Just their presence. Just by being a charged particle, you have a field around you. And if somebody enters into your field, you exert a force on them. Okay? So when we say a field, we are saying it's a region, right? If you have a charged particle, let's say like this, you're going to learn more and more about it. Let's say you have a charged particle, a positive charged particle. We are saying there is a region, okay? And this region, they say that it goes all the way to infinity. So it's a big region. It goes all the way to infinity. And if another charged particle enters there, which is already, there are many charged particles in that field, because if it goes to infinity, then it includes everybody. If you have two charged particles in the field, they are going to exert a force on one another. Okay? And that force is going to be your electric force. Now, this is also the reason why we see atoms or we see ions bond in chemistry. Okay? Chemical bonding, this too. You know, ionic bonding, people say it is the transfer of electrons. Let's say you have a sodium. I'm going to just do it real fast. And you have a chlorine, right? Sodium is 11, chlorine is 7. So sodium will want to have 10 electrons. By giving away this one, it will remain being stable. Okay? It will have the same electronic configuration as neon. Right? Is it neon? I think it is neon. So if it gives away one electron to this guy, this chlorine guy will now be stable again. Right? Chlorine will also now be stable. So these guys are going to agree to say, okay, what should we do for us to gain this? I'm going to give you 1, and you are going to become stable. Is chlorine 7 or 17? I'm not sure. Is it 17? I think it's 17, right? Whatever number it is. Yeah, I think it's 17, so that it becomes 18 like argon. So sodium will give 1 electron, and sodium will remain as Na plus because it has given 1 electron, but now it has 10 electrons. It is stable, but it is now charged. So it is stable in terms of the number of electrons, but it is now charged. It was neutral, it is now charged, yet stable. Now this chlorine guy will become, it was not a Cl minus, it was a chlorine, Cl. Now because it has received an electron, it's now a Cl minus, right? It's now a Cl minus, although it is now balanced like 18. So this transferring of electron is not the ionic bonding. So that's why you cannot say ionic bonding is the transfer of electrons. Transferring electrons does not cause a bond. What then happens is, after this transfer, these guys are now oppositely charged. Can you see that? Sodium is now Na plus, chlorine is now Cl minus. So what do? They attract, because there's going to be a force between them that's going to pull them together. And that's your electric force. So electric force is the reason we see ionic bonding. It's the one that makes Na plus and Cl minus come together after the transfer of electrons, and they'll stick together, become NaCl, and that's a bond. So there is a force, and that force is the one that is responsible for what we see. Now here is the last line. It says it is long range. That's another thing you must know. It is long range and goes to infinity. So in other words, this electric force, all the charges are exerting a force on one another. Whether one is here and another one in Spain, yes, they are. But what happens, what you must know is it decreases with distance. So at some distance, it is still there, but we count it negligible. It's so small, okay? Although it's always there. When we say it extends to infinity, we are saying it is always there between any two charged particles wherever they are. But because it decreases with distance, according to Coulomb, which we're going to see just now, because it decreases with distance, when it gets to a certain distance away from, when the charged particles have been separated by a certain distance, it becomes negligible. It's so small, okay? So never forget that. But it is always there. It extends to infinity, but it decreases with distance. Now let's see how to then give this electric force a value. We want to give it a value. We want to be able to calculate it, find its value. And the guy who did the breakthrough was called Charles Augustin de Coulomb. He was from France, a French physicist and a military engineer. When we say a military engineer, somebody who designs things for war, right? Many things, not just the machinery, the equipment, but they are the ones also that go and remove bombs from a field. They're the ones that design the path for the trucks to move in war. They're the ones that, because if you use the wrong path, your machinery can get stuck in the mud or whatever. So these guys choose the best roads to travel with your equipment, big, heavy equipment for war. And not only that, but they're the ones that help design effective trenches for soldiers to fight from. Trenches are still being used in wars in 2024, just so you know. As long as it's a physical battle, then soldiers will probably use trenches. So yes, Charles Augustin de Coulomb was a military engineer designing military stuff. He did many things, okay? He did many things. He also was, he also studied the strength of materials. He was checking strength of different materials and helping engineers to choose the best material to build whatever they want to build, to make sturdy structures, strong structures, okay? He was studying that in his life again. But what we normally remember him for, what his biggest achievement was in electrostatics, studying electricity. What did he do? He conducted an experiment in the 18th century. 18th century is from 1701 all the way to 1800, right? So somewhere in the late 18th century, or 17 something, right? 1785, 1786, somewhere in the late century, he did an experiment. And what was he doing? He was trying to investigate the relationship between charges and the force they exert on one another. What is the relationship? What are the things that affect the force between charged particles? How do they relate to one another? And he did meticulous measurements. Meticulous means careful. He was doing it well documented, writing down every step, doing wonderful experiments, writing down everything, trying to analyze what is happening. And he discovered 4 key things which we use today to know the formula for electric force. And because he's the one that did it, we call that Coulomb's law. Coulomb's law is the formula for electric force. Okay, it is the one that helps you find the magnitude, the size of the electric force. We find it using Coulomb's law. So if you want to find the size of an electric force, you have to use Coulomb's law. No way around it. That's the only one that's there. So here he discovered the force between 2 charged particles is, let's see what he found about the force. He found out that this force, point number 1, is directly proportional to the product of the charges. The force between 2 charges is directly proportional to the product of the charges. So if we were to put it, we would say the force is directly proportional to charge 1 times charge 2. Okay, that's fine. The force is directly proportional to charge 1 times charge 2, product of the charges, and inversely proportional to the square of their separation. And it is inversely proportional 1 over r squared to the square. Square means to the power of 2 of separation. Separation is r. So it is inversely proportional to r squared. So we say 1 over if we want to say inversely proportional, right? So we have these 2 things, and they are the ones we'll use in the calculation. We can combine them to say, that means we'll say force is proportional to Q1 times Q2 over r squared. That is it. Okay, that is what force it is proportional to. Is directly proportional to product of the 2 charges. Let's say the charges are 1 and 2, so we call them Q and Q2, and inversely proportional to the square of their separation. Number 3. What is the third thing? Well, these 2 things that we are now about to write are not really part of the formula to find the values, but they just work. The force exerted by one particle on another acts along the straight line that connects the centers of the 2 particles. So here, the force, you have these 2 particles, right? The force comes along a straight line that joins the centers of these 2. So the force is along this line that joins the centers. It is attractive if the charges are opposite, and repulsive if the charges have the same sign. So because they have the same sign, it will act along this line and it will be facing away. It is repulsive. It makes them all push away from each other, right? Okay, we know that if the 2 forces are different, it is attractive. When the forces are the same, it is repulsive. So now let's put it into a formula. Let's have something. So we said the closest we have so far is to say that the force is directly proportional to the product of the charges Q1 times Q2, and inversely proportional to the square of their separation, like that. Now what we do is, remember, we have a proportional to sign here. We can't use it to find an answer because it's not there. It's not part of a mathematical equation. So what we are going to have to do, let's not say mathematical expression, but we can say mathematical equation, okay, to find the magnitude. What we do is, whenever, I'm sure you've done direct proportion and inverse proportion in high school or wherever, when you want to remove this proportional to sign, what do? You multiply the right hand side by a constant. So in this case, we want to remove this fish and put an equal sign. We need an equal sign. Once you want to change from this to an equal sign, you multiply the right by a constant, something that has a value that never changes. So it'll be KE multiplying Q1 times Q2 all over r squared, and this is the force. Okay, this KE can also be called KC times sometimes. It's the Coulomb's constant. Okay, it is the Coulomb's constant, right? And it has a value because any constant has a value. So definitely it has a value. And you say to me, what is its value then? Because you're saying it has a value. Coulomb's constant is equal to, this one you have to remember, 8.987. In calculations, they sometimes use 8.99. And then this is times 10 to the power of 9. Then newtons, right? Meter squared per coulomb squared. You see where these units come from. But for now, just remember 8.99 times 10 to the power of 9. This is going to be your Coulomb's constant Ke. And then you're going to multiply with these other two, and then you will be done. So this is the electric force, and that's the formula. Now, this electric force is very similar to the one that Newton had found a few years before that. Like when I say a few years, I don't know, it's about 100 years before that, I'm not sure. But yeah, it was it was quite a long time. And Newton had said his formula is for gravity. He says the force due to gravity, so let's call this electric force Fe, force due to gravity is proportional to the product of the masses m1 times m2, and it is inversely proportional to the square of their separation. Because look, gravity works on masses, things that have mass. Electric force works on things that have charge. What do we mean by things that have charge? Things like electrons, things like ions. Ions like what? Na plus. This one is a charged particle, so we call it a charge. When we say charge, we mean a charged particle. An ion. There's an ion. We have Cl minus. It is an ion again. So because it is an ion, we have a force. Okay. This one, an electric force acts on this charged particle. If we have just an electron, an electric force works on this charged particle. So that is why these charged particles can be used to conduct electricity. Okay, we have our electric force acting on them. Now, gravity acts between two things that have masses. So instead of Q1 times Q2, we say M1 times M2, and we don't have to put modular signs. You ask me, why did you put modular signs? Modulus means we don't want the sign on Q1 and Q2. I didn't put modulus. I put modular signs because we only want the size of the charges. If the charge is negative, something comma something, when you put in the formula, ignore that negative. Just make it 4 point what. Because we only want the size to find Coulomb's law. Are we together? We only want the size to be able to find Coulomb's law. Now, what you must know is in Coulomb's law, before I leave it, these charges, this Q1 you're going to get, is normally going to be in microcoulombs. So you're going to have to know your table of prefixes to know that micro means times 10 to the negative 6. So you change it, it'll be times 10 to the negative 6 coulombs. Let's say it was 7 microcoulombs. This will become 7 times 10 to the negative 6 coulombs. We're going to see in the next few videos that you actually have to always convert your units to SI units. So that means you're going to have to remove that micro. You can't put it in the calculator. Whilst it's there, it's going to give you a wrong answer. It will give you a wrong answer. All right, now this force of gravity is m1 times m2 over r squared again, which means we'll say Fg is equal to, instead of K, we put a constant because we want to remove this guy and put a constant. It'll be now a G, capital G, not the small one we used to. So it'll be G m1 m2 over r squared. In here, it's K q1 q2 over r squared. So these are the two guys. Remember them. Don't forget them. If you know them, then we have half the job done. Okay? Goodbye for now. See you in the next video.